Hi, I'm Irvin Miller. I'm director of the Math and Physics Exploration. I've been working on some problems in maths over the past few years that I would like to share with you. In past years, you may have heard some discussion about fuzzy math. One of the things that I was concerned when I was learning math was letting others think what was best for me. I looked at education and found that what it was really doing for me was to teach me to accept a group consensus. And over time, I learned to challenge what I was taught. And I'd like to share these with you on the next few slides. In 1925, physicists thought they fully understood physics. Then in that year, Heisenberg and Erwin Schrödinger discovered a whole new way to model the basic foundations of physics. Mathematicians Gödel in 1931 and Cantor in 1874 did the same thing for mathematics with the incompleteness theorem and the concept of infinity. Yet, today we still not have fully embraced their insight. We are taught to accept another person's interpretation without challenging the validity of that interpretation. While mathematicians may be abstract, we use models and applications to give us a feel for that abstractness. We use different problem-solving approaches to validate our interpretations. We are going to undertake an expedition to show you why we must challenge the foundations by showing you that zero is not nothing, that it has a sign, and that its significance is not that of a placeholder. We are going to begin with that numbers are not unique by disputing the commutative nature of numbers. We have the expression 3 plus 5 equal x, where x has one solution, 8. We accept this for integers, but can we accept this for decimals? We have a simple decimal, 1/5, can be represented by 2/10, in which we say that 1/5 and 2/10 are equivalent. Now let us look at 2/3. The difference here is that the decimal equivalent goes on forever and ever. If we multiply the fractions that represent 0.66, 2/3 times 2/3, we get 4/9 is equal to 0.444, which goes on forever. However, if we use this in a different way and start off with just 2 digits, we get 0.36 as an answer. We go to double digits, we get 0.356. We go to triple digits, we get 4,43556. And when we go to 4 by 4 digits, you begin to see a pattern where we have a group of 4s, a single 3, a group of 5s, and a 6. Obviously, 0.4444 is not equal to 0.4444, 3, 5, 6. Though through the concept of limits, both of them approach 4/9, but they never really equal to it. And the difference between the limit and these numbers is not the same. For that matter, we could choose 0.4444 going on indefinitely, followed by some 7/7/8, and that would also approach 4/9. We know that 0.666 can also be written using an infinite geometric series. Can be written as 0.6 times 1 minus 0.1 raised to the third power divided by 1 minus 0.1. And if we do the arithmetic, sure enough, that gives us 0.666. If we now take the 2 using those particular formulas, we get what we've normally gotten, an infinite row of 6s, an infinite row of 4s. However, if we multiply those equations times each other, we get a different result. And what we see now is that factor of 0.1 raised to the third power. Now, when we square it, it becomes three parts. That's the major change. And normally what would happen is we would assume that 0.1 to the nth power and 0.1 to the 2nth power would go to 0. And they do. But look what happens when we do the multiplication. We end up getting that same series we did using an approach of increasing the digits, contrasted to using an infinite series to generate those digits. Now, there's an anomaly. In base 3, 2/3 can be written as 2 times 1/3. And in base 3, what we call 1/10 is 1/3. And if we multiply 2/3, but what we want to do is we want to look at 4/9. And what we see for the 4/9 is that it's 1/3 plus 1/9, which in the base 3 system is 1/9 over 1/81st, or 1/3, I'm sorry, over 1/9, which comes out to 4/9. So in the base 3 system, 0.11 looks. Now, in this case, we don't have infinite decimals. So we don't have a problem like we did before. So it seems to be the infinity that gives us the problem. In order to resolve this number, we assume that the number is an approximation, sort of an uncertainty principle. 4/9 can be written as 0.444 plus or minus 0.001. The answer lies between 0.0045 and 0.4443. And as we get more digits, we get a more precise answer. This is not a novel concept. For example, the population of the United States on July 2026 was 342,691, 342,691,076. Well, during this period of time, there are 3.1 million births and 3 deaths and 3.6 million births, which gives us a change in the population of 500,000, which means all those extra digits don't mean anything. So what we really find is we would write that number as 343 million, which the changes would be hidden. Even in measurements, if we make a rectangle the size of 1 inch, the theoretical length of the hypotenuse is 1.44, which is the square root of 2. But the square root of 2 goes out to 1.4142 indefinitely. When you try to measure better than 1.414, you would have to use a vernier to get to that actually, which most students do not know about anymore. But there's a limit to how well we can measure things. Most often we let someone else do the thinking for us. We can illustrate the commutative property for integers that can be derived from distributive property. For example, 5 times 1 can be written as 5 ones. Well, the 5 ones can be written as 5, which is the same as 1 times 5. So 3 times 5 is 3 5s. Each of those 5s can be written 5 times 1. And when we use the distributive property, we get 5 times 1 plus 1 plus 1. And that's equal to 3. So 3 times 5 is the same as 5 times 3. This is for integers. We assume that it holds for other numbers. We illustrate that infinite decimals are not quite unique, and we're not commutative. We know that we now take the following example in a different area. We raise 4 to the first power, which we know is 4. We're saying everything to the first power is 4. But 1 could be written as 1/2 times 2, or 2 times 1/2. And if we follow through those calculations in the first line, we will always get 4 as the answer. But in the second approach, if we change the 1/2 times 2 to 2 times 1/2, we can get either -4 or +4 as an answer. This example is showing that fractions are not commutative, but mathematicians just put that aside. Let us take a moment to philosophize. We start off intuitively questioning what I was taught about the commutative property for multiplication. This began with the definition of multiplication being a counting process, that multiplication was not commutative for matrices and quaternions. I then discovered that it did not apply to fractional exponents. This then led me to redefine the multiplication process, where I threw a zero in there. This allowed me to show that 0 times 5 was 0 using pattern recognition without having to assume the multiplication was commutative. Then I read the negative numbers. We're not counting numbers. I then considered the negative sign as a vector. When you counted the numbers as you do with positive integers, and then flip them for each negative sign in the multiplication. So 2 negative signs would become a plus. What I was doing is now making up my own postulates and proving that they gave the same results as the traditional methods, but they explained the results that the traditional methods could not explain. The key to this thought process was to find different approaches to get some of the same conventional results. Then Zeno's paradox emerged. It was an alternate way of solving a problem. The real goal, turns out, that we wanted to determine the time needed to catch the rabbit, if you're familiar with the Zeno paradox. The non-uniqueness of decimal representations of fractions then emerged. After showing the fallacies in the traditional approaches, I had to find several ways to look at the problem to convince myself that my viewpoint was correct and consistent, and that you should accept it. This arose out of the importance of checking your work. Thus, I showed how numbers were really approximations of the quantities that we were measuring. We could not get an exact answer, but we could get pretty close. We have all been intuitively aware of this. We may just not understand why. In my conquest for better understanding math, I came across a video, Zero to Infinity. Despite the rave reviews that this film got, I disagreed with the interpretation of every concept by the renowned mathematicians in the film. This bothered me a little bit, because why should I be right and everybody else be wrong? So let's begin. The claims that 0 is nothing, 0 is special as a placeholder, and that 0 do not have the sign, I did not believe. But I did discover that 0 is really a reference number. The film started off with saying that because 0 plus 5 equals 5, 0 must be nothing because it didn't change the value of the 5. It gave the same answer. However, 1 times 5 equals 5, and we know 1 is not nothing. Furthermore, 5 to the 0th power equal 1, and 0 factorial equal 1. We would have expected them to be nothing if 0 really was a representation of nothing. This was a mystery, why this statement about 0 being nothing was being said today, when in our textbooks, we state that 1 is the identity element for multiplication and 0 is the identity element for addition. This gets around 0 being nothing, but it's not enough for me. But I am not satisfied by this explanation either. We know that we can create numbers to add 1 to the previous number. 1 plus 1 is equal to 2. 1 plus 2 is equal to 3, etc. Then what number that is added to 1 would give us 1 as an answer? On the number line, that is 0. And on the clock, that number is 12. Now let us apply this concept. 0 plus 1 is 1. 2 plus 1 can be replaced by one of the zeros by 0 plus 1, or the ones. And then we regroup, and we get that 2 is equal to 0 plus 2. Using the commutative property, we show that the 0 added to any integer gives the same answer. In this case, we didn't use the commutative property. We used the associative property. Since 0 plus 1 equal 1, then 0 is equal to 1 minus 1 by subtraction. But we also could subtract 1 from both sides, and we get 0 plus 1 minus 1 is equal to 1 minus 1, and we saw that 1 minus 1 is 0. So 0 plus 0 is 0. Makes us feel a little bit comfortable because it's consistent with adding 0 to non-zero numbers. Note that we had defined zero subtraction in 2 different ways. This could be a subtlety undoes my argument. By the traditional way of multiplication, 2 times 0 is equal to 0 plus 0 equals 0. On a clock, we would have 2 times 12 equal 12, going around the clock twice. The reference point interpretation resolves the anomalies, even for a geometric viewpoint. Here we show a line 1 unit in length and another line 2 units in length. And when we want to add them, we just take and put the tail of the arrow of one on the head of the other. So each arrow has a starting reference point, and one of those reference points is used to connect the two arrows. So we can see that the answer of 1 plus 2 would be equal to 3. And we notice there with the first arrowhead that that point at the end of the arrowhead represents either a 1 from the length or a 0 from the reference point. The 1 and 0 on top of each other. Even while thinking of 0 as nothing, we are still able to explain and solve lots of problems. But do we have a real understanding of 0? The reference definition with the associate property then redefines multiplication. So we show that 3 times 5 is not just 3 5s added together, but 3 5s added to a 0. This is important because we can use pattern recognition to show that 0 times 2 is equal to 0 without invoking the commutative property. So we see on the left that 2 times 2 is equal to 0 plus 2 2s. 1 times 2 is equal to 0 plus 2. Each time we're dropping 2 as we move down to the next line. So dropping the plus 2, we get 0 times 2 is equal to 0. But if we write in the conventional way that 2 times 2 is 2, the first time we drop a plus 2. But when we get down to the 1 times 2, the only thing left is to drop a 2. And that leaves a space. Is that space 0? We don't know. Another argument given in the 0 to infinity film was that 0 is a placeholder. So if we took the 0 out in 203, we get 23. But 8 also could be a placeholder because we take the 8 out, we get a 23. So I'm not quite sure I understood that argument as a placeholder because it seemed to focus on that 0 is a placeholder, sort of ignoring the other numbers. But let's look at multiplications. We have 111 multiplied by 505. The first line would be 555. The next line would be 4 zeros, and the next line would be 2 zeros and 3 5s. And we add those together and we get 56,055. But if we don't use 0 as a placeholder, then what we do is we multiply 5 times 111 and get 555. And 5 times 111 is also 555, but it's been moved over 2 places. So we move it over 2 places. We don't need 1 zeros in there to hold the places. The numbers above it are actually holding the places. Using 0 as nothing in a placeholder makes multiplication more difficult to solve. Now let's look at another example. 2.30 is equal to 2 times 1 times 3 divided by 10th plus 0 over 100. That's using number structure. We get 2 plus 3 over 10. And 0 divided by 100 is 0. And 0 added to any number, pushing this a little bit, gives us the same number. So 2.30 is the same as 2.3. 2 different representations. They must lie in the same place on the number line. That's a little bit easier to accept. But having minus 0 and 0 on the same place might be a little bit harder to accept. Even where 0 might be a placeholder, we again show that the number is easier to read without the 0. I feel confident about my interpretation because I understand and explain your interpretation and show the fallacy. And now what about 0 having a sign? Well, when I was in school, they taught me that 1 divided by 0 was infinity, and the way they showed it to me as x approached 0, as we show on the left, 1 divided by 0.001, the result keeps getting bigger. So for approaching it from that side, we get plus infinity. But then I read somewhere on YouTube, somebody says, well, you could approach it from the other side. And if you approach it from the other side, you're coming in with negative numbers. So 1/0 could be minus infinity. Now, people seem to be aware that there was an anomaly to start with, but they didn't think about signs. We define negative numbers as follows. A negative number plus its positive inverse added to itself is a zero. And from that definition, a negative number is equal to zero minus a positive number. Here we show it with a number specifically that -2 is equal to 0 minus 2. If we substitute zeros for the 2, we then see that minus 0 is equal to 0 minus 0, because that's the notation for negative numbers. We know that 0 plus 0 is equal to 0. If we subtract the 0 by moving to the other side, we get 0 is equal to 0 minus 0, which we now know by notation is a negative 0. Well, 0 equals a negative 0. They must be in the same place on the number line. That is how I interpret that. We have to be careful with the proof and argument, since 4 to the 1/2 power square root of 4 is equal to plus or minus 2. Then is 2 equal to minus 2. So there was a little bit of subtlety in there, or else we could come out with something that both of us would disagree with. Observation tells us no. We can see that as we get closer and closer to 0 from either side, we are getting closer and closer to that number. But when they reach one being on top of the other, it is not too far fetched. The main purpose of this interpretation was to explain the function 1/x and x equals 0 or minus 0. I feel confident that my interpretation of 0 number structure should be the standard accepted approach. Does it make a difference in our understanding of math? For me, it does. I just wanted to go into some other area just to show that this foundation of math really has to be examined more carefully. Complex numbers are as much a part of our number system and structure as our negative numbers. Like in negative numbers, they are vectors. They were discovered when we did not have a structure to explain the square root of a negative number. Addition is associated with translation, multiplication with magnification, and exponentiation is associated with rotation. This interpretation brings this temporarily to a closure with number structure. Complex numbers are orthogonal to everyday numbers when the real part is 0. We generally like to ignore complex numbers because we feel they are alien to our everyday number structure. There's a problem. 5 raised to the x power plus 25 raised to the x power is equal to 30. Well, that could also be written as 5 to the x power plus 5 to the x power squared. Okay, and the answer we find is if 5x is equal to 5, then we would have 5 plus 5 is equal to 30. But if 5 to the x power is equal to 6, we have -6 plus -6 times -6, which is plus 36. Minus the 6 gives us 30. In the first case, x is equal to 1. In the second case, x is equal to, after doing arithmetic, I pi plus the logarithm of 6 to the base e divided by the logarithm of e to the base 5. I checked it on a calculator. So somebody else agrees with me that that is a correct answer. I have looked at dozens of YouTubes. Most of them ignore or are not aware of the second solution because they are taught that you cannot find the logarithm of a negative number. We went from 0 to negative numbers to complex numbers. The consequence is that you cannot find a solution to the problem that is almost second in nature to me. The application of the completeness of mathematics should have the same impact as the uncertainty principle of physics. maybe math is fuzzy. So I've taken you through a session in which I feel comfortable with the approach I look at is a better presentation than approaches that I've read about already. What I'd like to do is have others agree that that's the case. That's why I've made the presentation to the arguments. So now you either agree with me or you don't agree with me. Thank you for taking the time to listen, and maybe we can talk later.